All right, so here in this particular video, I have a few rotational dynamics question for you to practice, or MCQ here for you to practice. All right, so hopefully watch and keep up. This first one, it says there are two wheels, A and B. Here's the diagram for it. It says the radius of B is 4 times that of A, and it wants us to find the ratio of IA over IB, or the moment of inertia of IA relative to the moment of inertia of wheel B. And it says that both of these have the same kinetic energy as they spin. Okay, all right. So let's go and do it. Generically, the function for KErot is just 1/2 I omega square. I'm just going to apply this function twice, one for wheel B, one for wheel A. That's it. So here I'm just going to go ahead and go KErot for wheel A on the right is just 1/2 IA omega A square. And I'm going to go ahead and do the same for wheel B. So same statement, except the subscript here is B instead of A, okay? But you notice here in my work, KErot and KErot do not have subscript because the problem clearly states that they have the same rotational kinetic energy. So when things are the same, leave subscripts out because KErot is represented by 1/2 I A omega A square, but KErot is also represented by 1/2 I B omega B square. You can set these two functions equal to each other because they represent the same KErot. So I'm just going to go ahead and carry these two statements down in my work. The 1/2 is pure on both sides, so I'm just going to go ahead and do that. And then you notice here, though, we have IA, IB, IA is on the left, IB is on the right. We want IA over IB, so I'm just going to go ahead and divide both sides by IB just so it looks like the ratio that the question asked for, okay? All right, so I'm going to divide both sides by IB. At the same time, I want to divide both sides by omega A square. So I'm going to bring IB from the top to the bottom, to the bottom left, and then omega A square in the top left to the bottom right, and that's where the statement comes from. So at this point, in order to find IA over IB, I need to find what the angular speed for wheel B is and the angular speed for wheel A. But that's super easy to do. All you have to do is apply the, well, I like to call it the bridge function, the relationship between linear velocity and angular velocity, okay, simply by multiplying it by r. All right. So from here, I'm just going to apply this function to B and A. So no particular order. I'm just going to go ahead and do that. Well, I made a note for you here. This is important. As the two wheels spin, this conveyor belt or this belt is a single item, so it has to have the same linear speed throughout. Okay, so every point on the belt that is moving has the same linear speed because it's one single object. So keep that in mind. This is important. Otherwise, you might sit there and things different and goof. All right. So here V is equal to R omega. You notice here V don't have a subscript. That's because the speed of the belt is a single speed as it wraps around these two wheels. So I'm going to do the same on the right side. V is also equal to RA omega A. And then from here, I can just go ahead and find omega B and omega A and then just substitute it down here, okay? So on the left side, I'm just going to isolate for omega B by dividing both sides by RB. That's what it looks like. On the right side, I want to do the same skill. I'm going to solve for omega A by dividing both sides by RA. However, you notice here, we have V on top on both these expressions, except on the left here, you have RB. On the right, you have RA. You have three unknowns. You have a V, which is one unknown. You have RB, which is the second unknown, and RA, which is the third unknown. However, there is an important conditions given in the problem, and that is the radius of B is 4 times that of A. So I'm just going to get rid of RB by substituting out for a true statement, okay? So RB, I'm just going to rewrite as 4RA because that's what it said so. All right, other than that, I'm just going to go ahead and plug it in by using parentheses. So here on the work on the bottom, instead of omega B, I'm just going to replace it with V over 4RA. And again, all that's going to go in parentheses and the squares outside. And likewise with omega A as stated here is V over RA, so that's where that stuff comes from. Use parentheses, and then you're going to distribute this exponent to the top and the denominator on both top and bottom terms. And then if you do that, you get, well, the V here has an imaginary 1, so 1 square is just 1. And then 4 square is 16, so that's where the 1 over 16 comes from. And then you notice here you have V square over RA square. And on the bottom, if you distribute the exponent to the V and also the exponent to RA, you get V squared over RA. But really, you have two same terms here, top and bottom. You can just cancel it out. So the only thing left is just 1 over 16, which matches answer choice E. Okay, moving on. Now, here's the second one. Here's a solid cylinder with some mass m, some radius r, and it travels down some length of the ramp, which is called L, and it's from some height h initially, and wants to find the speed of the center of mass of the cylinder. So for this one, you have 5 expression here for the center of mass, or for the velocity of the center of mass. So we have to just figure out which one matches this particular shape. Okay. All right, so I'm just going to start with conservation energy because the solid cylinder is placed at the top of a ramp, which implies that it has gravitational potential energy to start. And once it reaches the bottom, all that PE is going to be converted to KErot and KE linear because it traveled linearly to go from top of the ramp to bottom. But as it does that, it's also rolling, and that rolling motion is called rotational. So on the left side, the initial energy is simply PE due to gravity. It wasn't moving, so all the K term is 0. So really, if you think about it, this makes sense. At the bottom, though, the only energy that exists is KE linear because it is moving linearly and is also rolling. So it has to have KErot. There is no PE due to gravity because there's no height because it's at the bottom. Okay. I'm just going to go ahead and expand this to mgh by definition of PE due to gravity. K linear is just 1/2 mv squared, and then KErot is just 1/2 I omega squared. And then from here, I'm just going to keep expanding. Okay. Left side hasn't changed. K linear gets carried down. The moment of inertia generically is CMR squared. C is the coefficient of the object relative to the axis of rotation. So here we have a solid cylinder that's rolling down, and as it rolls down, the axis of rotation is going to be the center of mass there for it. So I'm just going to go ahead and cancel m's out here. Okay. M's appears in all terms, so make sure you cancel stuff out properly. Here, M appears in every single term, so I can go ahead and cancel that out. Because I cancel it out, choice E doesn't make any sense because choice E has a mass in it. The fact that I cancel out mass just say that it's mass independent. Okay. All right. Now, to get rid of this omega square, because ultimately you're trying to find V, this term has a V, but this term right here has an omega, so we need to get this omega to V so we can combine like terms and factor out V. Okay. Once again, I'm going to go ahead and use this bridge function, v equals r omega. I'm going to isolate for omega because I need to get rid of it. So omega is just v over r. So down here, wherever omega is, I'm just going to substitute in v over r. So if you do that correctly, you'll get v squared over r squared. Once again, omega is square. So if you plug in v over r, and then you got to square it, so v is square and r is also square. Okay. All right. Everything else is carried down. And then next here, I'm going to go ahead and cross out r squared there and r squared there because there's an r squared on top and r squared on the bottom. And ultimately, you have to keep in mind with these types of problems what terms matter and what terms don't. So you notice here, in my work, I've already crossed out m, and in the previous step, I just crossed out r. So I'd like to remind you, if you are in my class, that v is independent of mass and radius because they disappear in this particular statement. Okay, so from here I'm just going to clean it up a little bit. Okay, oh, by the way, I cross out d just because it has an r squared in the answer choice, which r cannot be because v is independent of mass and r. All right, so I'm just going to clean it up. So here, GH on the left gets carried down, 1/2 v squared gets carried down. C for a solid cylinder rotating about its axis of rotation and through the center here, it's just 1/2 mr squared. So that's where the 1/2 comes from. These are coefficients that you can find online. Okay. All right. Anyways, so all this right here is just 1/2 c v squared, but c being 1/2. So at this point, I'll just go ahead and do basic math for you. 1 times 1 is 1. 2 times 2 is 4. But then this is a 2. So to add a half and 1/4, you have to find common denominator. So that will give you 3/4. Okay. So if you multiply this by 2, 2 times 1 is 2. 2 times 2 is 4. 2 plus 1 is 3. And then the common denominator is 4. So that's where the 3/4 came from. So if you need to bust this out on a scratch sheet of paper, it's important to add fractions correctly. Okay. Other than that, this is 3 over 4 v squared. So if you clean it up, I'm just going to go ahead and isolate for v squared by multiplying both sides by 4, but at the same time dividing both sides by 3. So you notice here the 4 is now on top and the 3 is now on the bottom because I just multiply by the reciprocal. At this point, I think I can stop doing work because it matches with choice B, right? This is v squared, so to find v, you would just take the square root of both sides. But really, if you look at it, it's 4 over 3 GH, which match choice C. Okay, all right, that's that. So here's the next one. Here it says, what is the speed? Really, it's the same problem as the last one, except all the V's now all of a sudden have L's and sine theta. So if you kept up with my work in the previous slide, I'm just going to go ahead and use the answer from the previous slide. So here V is equal to 4/3 GH, but you notice here there's no H here. So I like to point out to you, these types of problems just require you to just see relationships between math. So here, theta, H, and L is given. So I can say sine of theta is equal to opposite, which is H, over hypotenuse, which is L. So that's where this statement comes from. Sine of theta is equal to opposite, which is the height of the ramp, over hypotenuse, which is the length of the ramp. So from here, I can just go ahead and solve for H, because in the previous statement, in the previous slide, V is 4/3 GH, whatever the initial height is, but all the answers have been changed so that it has an L and a theta. So I'm just going to get rid of H just by doing basic algebra or geometry here, and then wherever H is, I can just substitute an L sine theta. So that's where this statement is going to come from. So it'll be 4/3 G, and instead of H, it'll just be L times sine theta, and it matches with choice A, okay? It'll be 4/3 times G L sine theta, and that's that. All right, let's do the next one here. Here, it says a solid cylinder has a uniform density, and then there's a thin cylindrical shell of uniform mass per unit area as well. All right, they have the same radius, length, and total mass. And it says if they're both rolling without slipping and with the same angular speed, what is the ratio of their kinetic energy relative to each other? So if you need to pause and read for this one, other than that, I'm just going to get cracking. So these are important conditions that I picked up. They have the same radius, same length, and then total mass. And then also they have the same angular velocity, right? So make sure you stick to conditions given to you in each problem and as they could change. All right, so KE total, once again, is just KE linear plus KErot. Now, why am I starting with this? Because the problem states that it wants us to find the ratio of the total kinetic energy of the solid cylinder to that of the cylindrical shell. So I have to find KE total twice, one for the cylinder, one for the shell. So I'm just going to start with generic statements here. KE total, once again, is just KE linear plus KErot. And then once you substitute out K linear, it's just 1/2 mv squared, and then KErot is just 1/2 I omega squared, and so on and so on. As I did before in this video, V is equal to R omega, so I'm just going to go ahead and swap it out. So wherever V is, I'm going to plug in R omega in parentheses, and then I'm going to distribute that square. So really here, it's just 1/2 mr squared omega squared plus 1/2. Once again, I is just C mr squared. C in this case, you have two different shapes, right? You have what is this? A solid cylinder and also a cylindrical shell, right? So C is going to be different for each one of those shapes. Now, if you look at this here, you have a 1/2 here, you have an M, and you have an R squared, and you have an omega squared. On this side, you also have a 1/2, an M, an R squared, omega squared. So at this point, I would encourage you to look at it and factor things out. I will factor things that are the same in both terms, right? There's a 1/2, there's an M, there's an R squared, omega squared. So I can factor all that out. So this right here would just be a 1 in the parentheses. And this right here has a C left, so that's what it would look like. And I'm going to box this because ultimately, because this particular problem, right, says they have the same radius, they have the same mass, and they have the same length. So really, M and R are the same. So the only thing that's really going to differentiate, that's going to matter a lot here, is just the coefficient of moment of inertia, the C that I highlighted here. So I'm just going to apply this function twice. So I'm going to do it for the solid cylinder. So I'm just going to carry this whole entire thing up. 1/2 mr squared omega squared, parentheses 1 plus the half is for a solid cylinder, right? That's where the moment of inertia comes in. Now I'm just going to go ahead and simplify this. 1 plus a half is 1.5. And I'm going to do the same skill for the cylindrical shell, right? So 1/2 mr squared omega squared, but for the coefficient for the cylindrical shell, it's just a 1. It's just mr squared. So because it's mr squared, the coefficient is just 1. 1 plus 1 is a 2. So really, I'm just going to clean that up a little bit. Now, it wants the ratio between the two energies. So I'm just going to make this statement. KE solid cylinder, dot, dot, right, to KE cylindrical shell. Well, what is KE solid cylinder? The only thing that's going to matter is this right here, the 1.5 and the 2. Because both of these terms have a 1/2 mr squared omega squared, which means they'll cancel out. So ultimately, I can just say that it's 1.5 to 2. Well, you notice here, all the answers here don't have a 1.5 to 2, but all you have to do is be a little clever, and that is multiply both sides by 2. 1.5 times 2 is 3, and then 2 times 2 is 4. So the ratio is 3 to 4, and that matches answer A. There's a different way to do this if you like, and that is this, okay? I'm just going to start with this statement, right? KE total, once again, it's just 1/2 mv squared, but the v squared got swapped out for r squared omega squared, plus 1/2 I omega squared, and the I once again got swapped out for C mr squared. So I'm just going to apply this function twice, okay? But instead of factoring the 1/2 mr omega squared out, I'm just going to keep it. I'm just going to go ahead and substitute in C. All right, so for C for the solid cylinder is 1/2. That's where that is. So I'm just going to clean this up. The left term here hasn't changed because it's still 1/2 mr squared. 1 times 1 is 1. 2 times 2 is 4. That's where this is. Now, this is a half plus a fourth, and all these have the same variable. It's really, they're two like terms. So I'm just going to multiply this fraction here by 2 so that I can find the common denominator is 4. So 1 times 2 is 2, and then 2 times 2 is 4. That's where that 4 comes from. And then the second term here, the 1/4 just gets carried over because it already has the denominator 4. So 2 plus 1 is 3. And then 4 as the common denominator just gets rewritten as 3/4, okay? So here's 3/4. And then I'm just going to do the same for the cylindrical shell, but the coefficient once again for the cylindrical shell is just 1. So if you clean this up, right, this is a half, and this is a half times 1, which is just a half. Well, a half plus a half is just 1. So I wrote that 1 there just for visual effect. Otherwise, you can leave it out if you like. It's just mr squared omega squared. But when there's no number in front of a term, it's just assumed to be a 1. Right? Multiplying by 1 doesn't change the outcome of the term. All right. So as you can see here, these are the two things I need, 3/4 and the 1. Well, instead of doing dot, can do this as well. I can say KE solid cylinder over KE cylindrical shell, which is the same as expressing the ratio in terms of dot. Well, what is KE of the solid cylinder? It's just 3/4 because I don't care about the mr squared omega squared because they have the same radius, they have the same mass, right? And they have the same angular velocity. So all these terms are the same. So I can ignore them for this particular problem. So make sure you don't just ignore it all the time. You got to make sure you read the problem, as is. All right. Other than that, the KE cylindrical shell has a coefficient of 1. So 3/4 divided by 1 is just 3/4. So really it's the same as 3 to 4 ratio, okay? I hope that helps. Stay nerdy, don't be whack.